think I would need to make this video, but people are burning down valuable infrastructure out of fear for their health. I'm sure you have heard all the insane theories. 5G towers are weakening the immune system and causing the global pandemic. 5G is causing cancer. 5G is mind controlled by the lizard people. I don't think I will succeed in convincing many of the lunatics that believe these things, so I'm not going to try. But let's explore what 5G actually is, how it works, and some of its real problems. Today, we're going to learn some interesting things about data transmission science and learn how our ability to transfer data through the air has evolved over the past 4 decades. Hopefully, we can pull a few of the people on the fence over to the side where rational people live in the process. We have been using different wavelengths of electromagnetic radiation to transmit information for hundreds of years. In ancient Greece, they used signal fires to convey messages with visible light. Today, we send messages with light through fiber optic cables. These cables are capable of carrying insane quantities of information and are the bedrock of the internet. But we can't connect all devices to it, because many devices need to be wireless. To make wireless data transmission possible, cellular networks needed to be developed, and it all started here in Japan in 1979, with the first generation cellular network, which we now call 1G. It began in Tokyo, where high-power radio towers would communicate directly with phones installed in cars. These towers used radio waves with frequencies sitting around here on the electromagnetic spectrum and simply transferred the data in analog. Let's see how analog data can be transmitted using a carrier frequency. Say we want to send a sound wave, a simple sine wave of 100 Hz. We want to apply it to an 850 MHz wave, a wave with significantly higher frequency. We can do this with amplitude modulation or frequency modulation, AM and FM. You have definitely heard of these terms before with radio stations. AM applies the data to the amplitude of the carrier frequency, so it will vary the amplitude of the carrier frequency, like so, basically tracing the original wave with its peaks and troughs. FM applies the data to the frequency of the carrier wave, like so, varying the distance between peaks to trace the original wave. To transfer a call using this method, you need a dedicated frequency band, defined by the lowest and highest frequencies used. If another user is using that frequency band on the same tower, then you need to use a different frequency band. The more frequency bands you have, the more calls the tower can handle. This is bandwidth. As the number of users grew, the system's capabilities were continually being stretched. Adding more frequencies to grow bandwidth is an option, but adding frequencies comes with its difficulties. Frequencies need to be licensed, and there is a lot of competition. Weather radar, military communication and security systems, GPS, television broadcasts, radio stations, radio astronomy, aviation systems, and air traffic control. They all need their own frequency bands. In order to gain new frequency bands, companies often had to go to auction and purchase the license with huge capital investment. This was done with every new generation of cell network, but a lot was done to cram more data onto a single frequency band through the years. Increasing the number of users that can use the same frequency band can be as simple as increasing the number of towers. Instead of using a single high-power tower to cover an entire city, multiple lower-power towers could be used. Frequency bands could then be assigned to individual customers within each tower's range without interfering with the same band in neighbouring cells. This increased the number of users networks could support, but it did not increase the data transfer rates. At its best, 1G was capable of 2.4 kilobits per second, but describing it in bits is a bit counterintuitive because, as we said, it worked in analog. Bits were the units of digital data. 2G ushered in a new era of mobile phones with the introduction of a fully digital system. Instead of encoding an analog signal into a frequency band, we encoded binary data. If you are like me, this was your first experience with cellular networks. My first phone was this beast, the legendary Nokia 3310. Sure, it could make calls, but digital data allowed for a new form of communication. This was the era a new language was born, TextSpeak. a language of gibberish invented to keep within the 160 character limit and prevent your mobile network provider from charging you for 2 texts. In English, each character in that 160 character text was encoded with 7 bits. Therefore, a 160 character text contained 1,120 bits. When 2G was first introduced, it could achieve 9.6 kilobits per second. It could handle that 1,120-bit text message with ease, but the 2G era lasted right up to the launch of the first iPhone, and speeds had increased to 200 kilobits per second thanks to improved internet protocols like General Packet Radio Switching or GPRS, sometimes referred to as 2.5G. By the time the iPhone 2 launched, 3G was the new hot topic. 3G introduced additional frequency bands. It's estimated that in Europe alone, companies paid over $100 billion in auctions to gain new frequencies. But 3G also made the change to a system that fully utilized the method of data packet switching, which GPRS utilized. Packet switching allowed thousands of customers to share many different frequencies far more efficiently. Here, data was split into smaller data packets. Each data packet contains a header, which contains the address of the destination and information on how to reassemble the data packets. Splitting the data into smaller bite-sized chunks allowed us to make better use of the frequency bands available. Instead of trying to find a large gap of availability on a single frequency band, we could split the data into small chunks and send it across many different frequency bands the moment a small availability appeared. Like changing from sending a huge truck of data on a single road to sending thousands of motorcycle messengers over roads with the least traffic. This made our use of the frequency band's capacity more efficient and allowed us to carry more data. As time went on, these protocols improved, allowing even more efficient use of the bandwidth. In 2005, High-Speed Packet Access, or HSPA, which you have likely seen represented on your phone as a H+, was introduced, which increased speeds up to 42 megabits per second. This was labeled 3.5G. 4G introduced a new technology called Long-Term Evolution, or LTE. It introduced even more frequency bands like the 700 MHz band that was previously used for analog TV broadcasts. It also introduced a new way of squeezing more data through the existing frequency bands with orthogonal frequency division multiplexing, or OFDM. OFDM allowed us to send far more data. You are probably familiar with the idea of constructive and destructive interference, where 2 waves meeting can combine and either enhance or cancel out the amplitude of each other. To prevent this, signals traditionally had to be separated out over time to prevent interference, but OFDM allowed the signals to be squeezed together and overlap, allowing the same amount of data to be sent over a shorter period of time. When the signals arrived, they were separated out and converted to binary data once again. How? I don't know. Magic or math or something. Honestly, the fact we can stream HD movies on our phone without a wired connection should seem like magic to the average person. It has gotten so advanced that we are now struggling to increase speeds without adding new frequencies, but there aren't a whole lot available. So, network providers are now reaching into the bargain bin and taking out frequencies nobody wants to use: high-frequency millimeter waves. Higher frequency waves have normally been shunned for these types of applications. Higher frequency waves just aren't as good at traveling. They get blocked by practically everything, including rain. Think of them like visible light. Unless you have a direct line of sight with a torch, you can't see it. To deal with this, network providers need to install huge numbers of transmitters. Studies have estimated that to bring 100 megabit per second download speeds to 72% population coverage and 1 gigabit per second speeds to 55% of the US population, about 13 million utility pole mounted 28 GHz base stations would be needed at a cost of $400 billion. Having this many base stations will help relieve congestion over a single frequency band, but 5G will also be using something called Massive MIMO, or Massive Multiple Input, Multiple Output. These are basically just groups of antennae that are listening and broadcasting to the same frequency bands. This would cause interference, but 5G is also looking to use beamforming, which will allow the antenna to aim at your phone instead of broadcasting the signal in all directions. This, coupled with the fact that higher frequency waves can carry more data, means 5G is reaching speeds of up to 1,800 megabits per second in the US. Higher frequencies can carry more information because we are encoding our information into the wave cycles. Our measure of frequency is hertz, but all 1 hertz really means is that 1 wave cycle is reaching us per second. 10 hertz means 10 wave cycles are reaching us per second, and 190 megahertz means 190 million wave cycles are reaching us per second. Because we are encoding our information into the wave cycles, that means we can encode more information into higher frequency waves. Up until now, we've been using frequencies between 700 MHz and 2500 MHz. So, 700 million wave cycles per second to 2500 million wave cycles per second. 5G will allow higher download speeds and lower latency. This will be huge for time-critical technologies like self-driving cars that require rapid communication between vehicles in the network and allow even more devices to join the network to create the Internet of Things. 5G has a lot of potential, and no, it's not dangerous. The electromagnetic spectrum starts on the far left with gamma radiation, which has very high frequency and short wavelengths. Higher frequencies and shorter wavelengths equates to higher energy, and indeed, gamma radiation does cause cancer. Anything over here you need to worry about. But 5G is operating all the way over here towards the lower energy frequencies. Yes, past visible light, which last time I checked, no one is afraid of. Yes, like visible light and microwaves, it's possible to cause heating with high enough powered beams of these wavelengths. This is the only non-crackpot theory I can find on 5G that actually sits in the realm of plausibility. The military even used high-powered 95 GHz beams in their active denial system, which just made the people on the receiving end feel like someone just opened an oven door in front of their face, and it could burn people if exposed for long enough. It's uncomfortable and was intended to disperse crowds. This was essentially a focus beam of 95 GHz light, akin to a massive magnifying glass focusing light to burn a piece of paper. Because yes, just as visible light can be used to cause heating, so can these wavelengths when used in high enough power and intensity. As we said earlier, these frequencies are blocked by rain, and so they certainly can't penetrate your skin, and these transmitters simply don't have the power to cause heating that would be damaging. They are simply too low power, and there are plenty of studies that show that they are not harmful. If you are afraid of 5G in this way, you might as well be afraid of streetlights because they emit higher energy frequencies. Everyday technologies like this can seem like magic until you peel back the layers to their earliest iteration and see that they are just the product of many years of problem solving, with each successive generation adding more complexity. If you'd like to learn more about the whole electromagnetic spectrum, including which parts are dangerous and which aren't, you should check out Brilliant's course that unravels the physics of waves and light. Inside, you'll learn things like how light can exhibit both particle-like and wave-like behaviors, how much energy electromagnetic radiation can carry, and even how to measure the speed of light. You can set a goal to improve yourself and then work at that goal a little bit every day. Brilliant makes that easy with interactive explorations and a mobile app that you can take with you wherever you are. If you are naturally curious, want to build your problem-solving skills, or need to develop confidence in your analytical abilities, then get Brilliant Premium to learn something new every day. Brilliant's thought-provoking math, science, and computer science content helps guide you to mastery by taking complex concepts and breaking them up into bite-sized, understandable chunks. You'll start by having fun with interactive explorations, and over time, you'll be amazed with what you accomplish. As always, thanks for watching, and thank you to all my Patreon supporters. If you'd like to see more from me, the links to my Instagram, Twitter, Discord server, and Reddit are below.